Hey everyone, in this video I'm going to show you how you can use Desmos to graph digital digits similar to the one that I'm showing you up here. What I'm showing you is a reference image. This is not a graph. It is to show you what I'm talking about with the digits in here. What we're starting off with is the center strip in the middle. There are some variations that I want to show you on how you can do this. And to lay out a rough plan, I want to show you how you can graph one where the sides are just straight lines. There's one where the sides are parabolas, and there's one where the sides are hyperbolas. So I am going to hide this reference image so it doesn't get in our way. And we're going to start with the center strip. Something that they all have in common is the lines that go across the top and the bottom. And so for that, I'm going to arbitrarily pick 2 points. And so let's do y is 1 and y is -1. Our next step is to connect them, and so to do that, for simplicity, I was thinking about using an absolute value equation that goes this way. For simplicity, we're going to go with y equals 2x, and you can control the slope of this. So if we want this centered more towards the right, or left rather, say -2, you would add 2 to this, and the line that comes afterwards will just be this same line but with a negative slope. And in this case we want for x to be between -2 and this point is -1/2. And we can copy the same inequality in here. We'll do something similar for the lines on the right side, and so this isn't +2 anymore. We want this to be -2. For the top piece, we want this to have a negative slope, and this is going to run from 1/2 to x to +2, since we're doing all the operations that we did on this line, but everything in reverse. And so we do the same thing with this line down here. No, I got it wrong. These two equations are the same, so this one must be the duplicate. It's going to be a positive slope. We move it to the right by 2, and it's going to be from 1.5 2x to +2. And what these inequalities have given us is that the piece in between is what we want to keep for the horizontal lines. And so that would be 1.5, since that's where this -1.5, since where this point ends, and it will end at +1.5, since that's where this line starts. And you can see there we have a basic LED strip using just the straight lines. Something that I like to do with this LED strip here is to pack these equations into piecewise functions, and so the top half will go into one piecewise function, and the bottom half will go into another piecewise function. So that would reduce this down to 2 equations. To do that, we would need curly braces, and you start with your first inequality. The order you put these in, it does not matter. I'm going to color code this so you can see it. So if it's between -2 and -1.5, you want it to be using this equation. That's the 2x plus 2 times the whole thing x plus 2. So it'll be a colon after your inequality, and you put this line in here. And you comma separate it, and you put your next inequality in here. So in this case, it's from -1.5 to 1.5. And if this is true, you want this to be 1. And then finally we have from 1.5 to 2. And that is this equation here. And I would like to not call this y, but rather call this f sub 1. Reason for the subscript is because we're going to have multiple functions, and this would allow us to manipulate. It will allow us to apply transformations to this piece here rather than having to go across the entire piecewise function and do component wise, because otherwise you might as well have stuck with this format. If you've been watching my videos in the past, you know that I like to define variables and constants to control dimensions and positions of our graphs. And so what I've defined in between cuts is a height variable, and so this is the distance between the top line here and the bottom line here. To make it smaller, it shrinks. Make it bigger, well, it widens. And W0 is the width of the flat lines you see at the top and bottom, and so to make it smaller, that's what it affects. And the W1 is the width of the larger line. So if you grow it, it gets wider. But in the case where W1 becomes less than W0, it will actually end up not showing up. And so you don't have to do this, but it does make for huge time savings. And something that I'll show you as an advantage with piecewise equations is applying transformations. So I'm making x0, I'll call it, make up some numbers here. I'll make a y transform. And now what we can do is hide these two. And what does strip call it? F1 of x minus. So if you call it F1 of x as is, this is the exact same line. But now you can subtract x0 and you can start translating this equation and do the same thing with y sub 0 here. And you notice that we didn't need to go through every single one of these fields and apply x0. We just put it in this function and it'll apply across the board. So this is why I opted for a piecewise equation rather than splitting them up like I used to do in the past. Plus, there's only 3 equations. If we end up having a bunch, well, that's a different problem. So do the same thing. F minus f of 1, x minus x sub 0, plus y sub 0. So now we just need to adjust these dimensions once, right? Make it not as wide or make it not as tall, depending on how you like it. And this will make it very easy to copy and paste all over the place. I'm going to recenter this at 0, and I'm going to leave the y up here, because the next thing that I would like to do is to show you a similar process, not with linear equations as the size, but we're gonna do quadratics next for those of you looking for something more interesting than just straight lines. All right, to figure out a parabola equation that we can use to build these sides, I want to explain what we're looking at. The blue and green lines define the heights that we have set earlier, and the 2 purple points you see is the slant. It's the slant that you see on the LED strips. What you'll find is that there is no single parabola that goes through 2 points. You need 3. So we'll still pursue the path of finding what paths through these 2 points. We'll end up with an infinitely many solutions. I'll show you what that looks like and how to adjust it to your liking, so that you can pick the parabola that suits your liking. To do so, the method I recommend is, since these 2 points are not both these are sitting at the x-axis. I'm going to go down a more generic approach to using a systems of linear equations. So the general form of a parabola, let's say, make sure I don't have a, b, or c defined as variables. That's the trap with having too many. Ax squared plus bx plus c. And we do have an x. It's w1 over 2. And we do have a y that's 0, so we're going to sub these 2 in for this equation here. And the other piece and we're need to do this again for these for this ordered pair. Let's sub these in. We have 0 equals. I prefer my y to be on the other side when solving systems of equations, and so this would be w sub 1 over 2, the whole thing squared, plus b times w1 plus c equals 0. And then the other piece that we have is, we don't need these. X is w0 over 2. In this case, y is h over 2. So our goal is to find an equation that describes all parabolas that can fit these two equations. Right, before we start solving for parabolas, there is one equation I forgot about. And the idea is that when we hit this point here, we want the derivative of the parabola to be 0 because as we want the parabola to start flat. And so we have a generic equation of a parabola that is ax squared plus bx plus c. And when we differentiate it, we get 2ax plus b, and the constant drops. And want for this to be equal to 0. And we only want this to be true when x is equal to this point here, and that's our shorter width. So that is w0 over 2. So now we have 3 equations with 3 variables. So we can expect our parabola equation to be unique in this case. So to solve this, well, since I'm doing this on Desmos and not on paper or on a paint screen, I want to duplicate all of these equations so that we have an original copy that we can go back on in case something does go wrong. And my recommendation when working this out is to go slowly and verify every step. And that's what our second set of equations is for. Let's start with the easy one. That's the one at the bottom. Let's solve for b, and because we can conveniently just subtract this term over and solve for b. Something that I'd like to see is our quadratic equations slowly come together. So I want to put the generic form of our quadratic equation up here, and we know that at some point b is going to be true, and so whatever value we find for a is going to come before this, and it is going to look as cryptic as, well, it's going to look even more cryptic than this, I'm sure. And so with this equation here, let's solve for c, and then we'll set these values equal to each other. So copy the value for b, and we'll mind the negative sign. And so now we're going to subtract everything over to solve for c. So let's subtract this over. And we're going to add this because we're undoing the subtraction. And we'll do the same thing over here. So subtract this term, but we add this term here. Now we can set these equal to each other and solve for a. So to do that, we need to move everything over to the other side. And so we'll do this one at a time by first subtracting this term here and then we add this term over because there's a minus in front. And to solve for a, we take h over 2, and I'm just going to show you just so you can see what we're about to do here. Every single one of these terms has an a in front, or it is multiplied by a, which means we can safely divide by the sum of all the coefficients. So it would be this term minus 2 times this value minus this number here plus this value. And something that I'm also keeping in check is that we have a negative coefficient for a. That's good because we want our parabola to be pointing downwards. So that is one way you can reality check. And now we're going to solve for c by subtracting this over. I'm going to preserve this here still. So c is minus this number because we want to subtract this to the side minus this value. And there you can see, let's put everything to the right of w sub 0 over 2, and we'll bring back the height. And you see that this parabola fits nicely with this. So, I want to repeat the same process with the other 3 parabolas. And I'm not going to show the whole thing again. I'm instead going to just cut right to the end. If you run into difficulties doing that process, do let me know in the comments, and I'll try to help the best I can. The process breakdown that I've shown is likely what I'm going to respond with. All right, if you're trying to save time like me, here's what I suggest. You save your hard work into an equation here, and then you define your domain. So that would be from w sub 0 over 2 up to w sub 1 over 2. Now what this allows you to do is now you can make g sub 1 of x, makes it again, make all the y's negative, and then you do it again, make all the x and y's negative, and a positive version of this. Our next step now is to put this all into a piecewise function. So to do that, I want to make an f2 of x. What I suggest is, if you have this already, I I'm going to delete it, but I would suggest on your graph you save it. So I'm going to delete the point since we were trying to debug. We don't need these two anymore. These three definitely keep. And I'm just cleaning up for you, though. So that you have documentation, I would suggest saving off the math you did, either on a piece of paper or on a WordPad. So to put in a piecewise function, so we're using F1 before, so let's use F2. And so for F2, we're going to go G sub 1 of X if it's between so we want for so we're going to delete this and we'll define the boundaries in here. So if this is between negative W sub 1 over 2, and that's going to end at W sub minus W sub 0 over 2, then we want this equation here. And if we're between minus W sub 0 over 2 and positive W0 over 2, then we want H over 2. And finally, if we're between this value and this value here, we want this to be G of X, G sub 1 of X. So now we just simply mirror the whole thing across the x-axis. So you have our second strip done with parabolas. So in the next part, I want to show you how you can piece these LEDs together. If you want to see a version where you use hyperbolas, it would be a lot more involved than a quadratic equation is what I'm anticipating. Though, if you want to, I'm leaving the door open for you as an option. So keep an eye out for a poll. And in the next part, I think I've already said this. We're gonna start putting these LED strips together to start making something like this image. Well, not this exact image, though. We're making these digits. And so for closing, if you did find this video helpful, do leave a like. If there's anything that you felt needed more explanation or better clarified, let me know in the comments, and I will respond as appropriate. Hope you found this helpful. And I hope to see you in the next part.